Okay. Good evening, all, once more. I can see some of you are already joined, and some are joining, or they will join as we kickstart the class. So now, this evening, today will be, or we'll be marking day 5 of our lectures. Day 5 of our lectures. So, and the topic for today is image restoration, feature detection, and pattern matching, which will be taken as Unit 3. So it is good to understand these 3 key concepts that made up of this unit. Under this, we'll look at a model for image degradation. We'll also look at noise. Under noise, we'll look at some of the subcategories of noise, such as salt and pepper noise, Gaussian noise, specklet noise, periodic noise. After that, we'll look into noise reductions and feature detection and recognitions, that is object detection basics. And this is what we'll be looking at, and many more as we progresses in the class. Hope all of you are following me.
Yes, sir.
Yes, sir. I'm following you.
Okay. So, in the word of introduction, we can deduce that image restoration is one of the major areas of image processing, as we discussed earlier. So this concept focuses on the removal or reduction of degradation, which happens during the acquisition of an image data. What are we discussing here? We are trying to justify that perhaps during data acquisition, data capturing, take for instance, you want to snap someone. There's a tendency that the image may not be sharp or blurred. The image may capture some certain background. The image may kind of have some spots. These are what we call degradation, that it makes the image to lose its clarity or brightness. Moreover, you can experience this. Maybe you snap a picture or an image clearly, and then maybe you printed it or you watched it and kept over a period of time. Maybe the time you visited your village, you take picture of your mom or your dad, which was a very long time. And at a point, there is a need. Maybe she wants to celebrate her birthday, or he want to celebrate her birthday. Maybe the picture was taken when she was young, and now she's old, and yet they want to put those pictures in the album or in a brochure or in a gallery. Because of the long time it has stayed, it will lose its brightness, its contrast, and the rest of them. Especially when you it was not kept well. When you pick it, sometimes when you have 2 or 3 put together, you see some of the things, it will be like it is gummy. It is washing out. These are what we call degradations. So you may want to find a way to restore the image. There are a lot of tools that can help you do that. If you ever visit video editing or image editing shops, you'll be surprised that a lot of things are taking place there where they are editing those images. Try to restore the image. So all these processes form what we call image restoration, ability to retrieve it, to make it lookable, to make it presentable, to brighten it. So that is why sometimes you look at some of maybe like obituary announcement or posters or flex banners. You see, sometimes if you look at it, it will not be bright. Why? It's just because maybe the picture have been taken over a period of time, a long time ago, and there's no way they can have access to current pictures. They decided to use the old one. Because of that, you look for a way to just to capture it, let it show the image of whoever that is going to see it. So all these processes, all the process it takes through which you bring back those images, you make it presentable, you make it for someone to use of it. They are collectively called image restoration. So anytime you have a very bad image, damaged image, and you want to bring it back, what the right word to use there, you want to restore the image. And we say for image restoration, other techniques require the use of frequency domain process or processes. However, in this unit, we'll lay more emphasis on the techniques for dealing with restoration rather than with the degradations themselves, or the feature of digital system which gives rise to image degradation. We shall also consider feature detection and pattern matching as we progress. A model for image degradation is more of mathematical models. Remember that the computer language is made up of zeros and ones. That is what we call machine learning. I mean machine language. So it is all about mathematics. It's all about models. Everything about computer is all about models. Whenever you capture image and then store your computer, we have the low-level language. I mean, the machine will then, what it does is it transforms those high-level language to a low-level language, which is the machine code, numbered zeros and ones. So anytime you capture or you type a text, the assembly language will be very busy converting it to a machine learning language. So remember, so anytime you see, when you talk about image, graphics, it's all about mathematical models. Take for instance, suppose we have an image function, we have X and Y axis, for which convolution with the image result in some form of degradation. Nevertheless, let's assume that H with the two coordinates X and Y has a single line of once, the result of the convolution will be a motion blur in the direction of the line. That is to say, the equations, these equations, G, represent the two coordinates, is equal to the functions of the two coordinates, which is x and y, multiplied by maybe the height of that coordinate. Where the asterisk you see is used to represent a spatial filtering. We cannot consider the noise, which can be modeled as an additive functions to the convolutions. Thus, if you use number of x coordinates, x and y, to represent the random error which may occur, we will have the degraded images expressed as g of x of y equals a function of two coordinates x and y multiplied by the spatial filtering, which is represented as asterisk, multiplied by this coordinate. So by the time you do it, you now transform it to have these equations. So, and if you write, if you pick the value of h and n and you have to rewrite using the functions, you can now have this. Just transform this by collecting the like terms. You pick the whole of this one, then when you compute it, you solve this, you'll be able to separate this from the general equations. You have f of two equations or coordinate ij. Then when you transform it, you have all of these equations, as you can see on the screen. So let's progress so that you may get to understand it more. We have noise. As I explained earlier, that when you are capturing an image, a lot of things that unusually may appear on that image, we refer it as what? Noise. We refer it as what? Noise. A kind of degradation in the image signal caused by external disturbance. So the external disturbance could be anything. It could be from the device, it could be the background. Maybe you take a picture when it is raining, or you took some pictures when the sun was so bright. The reflections from the sun, all of these could be for what we call external disturbance or disturbances. So, and it will affect the image. Sometimes you take maybe when the weather is dark or the light reflections, all these things could be associated with external disturbance. Okay. Just like image, if you see figure 3.2a, the original image pepper noise source, according to the Mark Andre 2004, which is the source. Then compare it with figure 3.2b, effect of salt and pepper noise. Okay, this was the original image. Look at the original image here. Do you see it? This is the original image. When those images have been dented, have been affected, that is the result of this, of the image. These are the results of this image. So how do you restore it? Let's move on to Gaussian noise. Is an ideal case of white noise. This can be saying that let's say N representing the noise, then we can model a noisy image by simply adding the two represented by, let's say, I plus N. If the image is represented as I, let's say I is the word image, Gaussian noise is what? The N. Just say I plus N, image plus the Gaussian image or the noise. With this, maybe if you are asked to explain what is Gaussian noise, you can use the formula to mathematically explain what it is by saying, just simply say Gaussian noise is a white noise which is normally distributed. For example, I plus N, where I is the image and N is the Gaussian noise. You are done with that and you have your full score. So the same way we have a speckle noise, which is mathematically represented for Gaussian noise. We model it by adding random values to an image. When they add a random image from what is existing to look at the effect of Gaussian noise, and this one effect of speckle. So all these things are, you can visualize it by seeing what we have here in figure 3.26 and figure 3.2D. Then periodic noise. This type of noise is used to describe the effect of periodic disturbance on an image signal rather than a random disturbance. Just like as I said to you, you snapped or you capture a picture or an image and kept it for a long period of time. What will be the effect? It will generate this periodic noise. The effect appear as bars over an image. Sometimes you see it even like something like the thing is burning or even be washing away. Sometimes if the picture is stay too long, it will be washing away. And look at the effect. Then noise reduction. Noise reductions. Here we want to look at, on the general note, filters can be used to remove or eliminate noise in an image. All these things work at the background level. Take for instance, in other hand, the edge that exists in an image usually produce high frequency components. If these components are removed or reduced in an image, what happens? The edge will become fuzzier. Media filter is ideal in removing impulse noise while preserving the edge. If you're using some softwares to do this, maybe you're using Photoshop applications to do this. Some of these are features that enable you to do that. When you click on this one and draw it and apply it, you check what you get, so that if you don't really want it, you can now increase it or reduce it. If I've done maybe engage yourself in any designing graphically, you see all this in the practical notes. So then media filtering. Here we are looking at how do you remove the removal of salt and pepper noise. The average is called the media filtering. The operations of media filtering, it helps you to what? To remove salt and noise pepper. Sorry, salt and pepper noise in an image. Example of nonlinear spatial filter. For example, using 3x3 mask as an example, the output values is median of the value of mask. Let us examine the table 3.3. Let's just see the table 3.3 for better usage. Table 3.3. Okay, maybe we'll look into that as we progress. All right. They say more of 3.3, but I can't find the table here. Maybe from those who prepare the material, because we are using the existing material to teach. All right. We can progress by looking at feature detections and recognitions. Generally, object detections. When you are talking about object detections, you use features to detect it. And it is very important topic of discussion when image processing occurs. When it comes the aspect of what image processing, object detection is very, very important. We can now deduce that the ultimate goal of computer vision is to design a system that would be capable of analyzing a scene and determining which items in a scene were relevant objects. Let me just summarize by saying the object detections helps one to determine which of the object that is harmful and which one is not harmful. It will enable to determine the harmful object and the one that is not harmful. This application of these object detections or recognitions have been embedded in different systems. Take for instance, in your car, most of the cars, newest cars invented, has object detection or what we call computer vision. If you are driving, if you are approaching, especially when you are reversing or you are turning and you are close to the gutter, it will give you a signal. The signal, the sense, it goes with the sensor. That sensor that is have been embedded in the systems is telling you while driving, you are approaching an object, and that object is very harmful because it has to do, maybe there's a potholes or is a gutter, or there are heavy maybe blockage, either tree or stones, or there are harmful objects that when you go closer, either you fall inside a gutter or you hit that object. This is areas that computer vision has made a brazen impact. You hear about robotics enabled with artificial intelligence, drone technologies. These are some of the sensors that enable you to detect it, some objects. If you use drones, there are a lot of sensors that have been integrated in that drones that will help you to be, you can use to deploy in some danger zones. There are places they call danger zones, especially in aspects of security. A place where if a woman goes there, it's not safe for such persons or for such security personnel. I remember when Boko Haram was order of the day, there what they call Sambisa Forest, that any of our Nigeria personnel or forces that goes there, most of them don't come back alive. That kind of a place can be designated as danger zone. Sometimes there are forests, when you go there, maybe some of they call it evil forest, where some spirits, people who committed atrocities are being casted away. When you go there, ordinarily, you may not come back alive. What if you are embarking on a research to determine how many people have committed atrocities in a particular community? And on your investigation, you discover that those who committed an atrocities or evil are being casted inside the forest. Some are buried alive inside the forest. Sometimes when we are watching some Nollywoods or some films, we see that some of the people who have been pushed or to be casted to the evil forest, what happens? Sometimes perpetrators are being left behind. Sometimes they will let the person up, or they will bury the person. Some hunters will come and excavate it and let the person up, and then push that person to the next village. So many things are in there to be discussed. But the idea of what we're discussing here is, if you want to carry out a research to determine what happens to the evil forest when somebody is cast away, or why is it called evil? You want to know the number of evil in the forest. You can carry it as a research using some computer knowledge or techniques to apply in there. And the aspect of the computer that helps you to do that is computer vision, using object detection, drone technology, and rest of them. Different sensors can be deployed too. So it is very, very important that anytime you are driving a car, it's giving you some sensing some images, some of the all these things. Sometimes even traffic technology. Today I was traveling to Jabi within the Abuja metropolis here, and we have to check through our Google map among the routes which one is safer. There are some of the routes tell us there is traffic or congestion in some certain areas. We have to divert it. What is happening there is a satellite image enabled with computer vision. It's helping to do that. And when you use your phone and you are pressing your Google map to check whether there's congestion on the road and the rest of them, you may not know what is happening there. All these are integrated sensors with your phone attached with the Google map, and you help you to simulate it. You simulate them and know where there is traffic or where there is no traffic. And this is the practical application of what we call object detection or computer vision. And while doing that, you use patterns to do what? To match the correlations between them. The pattern match is the pattern we're talking about. What sequence does it follow? Is it in linear form, horizontal form? You check y-axis or x-axis. Is it clockwise or anti-clockwise? All these things will help you to do what? To match. Which color are you using? Is it blue color that indicates congestion, or red color, or yellow color? So you should be able to know the color or what the color represents to enable you have a perfect or accurate matching of those patterns. So these are what some of the things you are seeing here. So some of the things you are seeing here, all of them borders about objects, borders about pattern matchings and the rest of them. For instance, now the location of the 6 tanks are now very clearly seen. The same type of process can be performed in the frequency domain. And look at 1, 2, 3, 4, 5, 6. Maybe you use your map and check. You see some white spots. You should be able to, what does those spots represent? Here we are saying that those spots are tanks. So this is how patterns can help you to understand what is happening in a particular scene. So other ones, and some of those in pattern matching, there are some limitations which envisage or cut or seen as accurate image of the desired object as it is likely to appear in the image. Changes in the object orientations and size will adversely affect performance. And finally, if the template image was taken in a different lighting than the source image, then the pixel values are less likely to line up, even for objects of interest. So these are few limitations that relates with pattern matching. So, and then in summary, where this unit covers the image degradation models, identifies sources of noise, as we have seen, and then finally it covers the pattern matching using some correlations. All right, you have an area for further readings on your own, can source out some materials, and even current in some recent studies, if you type that title in there, so if you're using Google Scholar, if you use scholar.google.com, if you type it to, which is purely for sourcing out for academic materials, you don't use normal Google, you use google.scholar.com, where you can now exactly get some current materials, 2024, 2025 materials on this. That would help you to get yourself current, because some of these source materials is just a kind of giving you how it generated. It's now less for you to make more research using some recent studies, 2024, 2025, and you can source it from Google Scholar and not normal Google. Thank you. All right. Finally, in our topic of discussion today is we'll look at module 4. And this module 4 is discussing about image coding with DCT and wavelength technologies. And the DCT, as we earlier discussed, represent discrete cosine transform. Discrete cosine transform, DCT. So we'll look at actually what the areas as it have been, where it have been applied. As we can see here that DCT have been applied in image compressions. Remember what we discussed about image compressions, image loosey and looseless images and the rest of them. So we say it has been applied here, though alternatively it has been transformed. Alternatively, you can transform it as wash, Hadamard, and wavelength. All these have been introduced on the course of this, where wavelength discuss about the features, the functions that are not restricted to the sine waves, which is quite actually different in form. So we'll look into it and then at the same time look at their characteristics. So by using those wavelengths, you should be able to have, you should be able to compare the high compressions with DCT based compressions. We look at the load rates and high compressions. At the same time, we will also discuss about the discrete cosine transform based compressions. Then at the end, you should be able to understand what is image coding with DCT. At the same time, explain the application of wavelength technology in image coding. These are the two things you should be able to, at the end of the discussion, should be able to figure it out. So, in the image coding, here we are looking at the common data transformation used in video compressions in the discrete cosine transformations. And it is in, look at some of the versions of that transformations. They are here. CCTITT, H.261, JPEG, H.320 group of standard for video conferencing. These are some of the which can appear both in MPEG 1 and MPEG 2. So we'll look into them as we progress. So I've told you that it's more of mathematics, which you take your time to go through the material and see how it works. Time may not actually permit us to detail them, but you go through it. If you have any challenges, you just in my YouTube channel where I will upload it. Anytime you go through it, you have any issues, always comment. Make your comment or drop your questions. It will be addressed. Okay, and at the end of the class, make sure, because I would ensure that I assess your performance based on what I see there. So I would want you to like that channel, then drop your name, so that by the time I'll be checking the assessment, I'll use whatever all the names I see there as an attendance, because I have to assess or grade your participation, and I prefer using it there, so that for those who could not make it to the lectures, they should be able to answer present by typing their names and possibly make any comment where necessary, and like the channel, so that I'll be able to assess your presence and grade you accordingly.
Sorry, sir. Can you say the channel again?
After the class, I will share it for some of you who are joining for the first time and all that. I will share it so that you make sure that you comment using your name and like the channel, so that once I see your like and your comment, I will use it to assess your or grade you. And after today's class, this is a day 5. Probably tomorrow we might meet to round up the class because of time, so that I'll commence your assessment and grading before the final revision class. So I'll share it once I am done. You'll get it through your mail. So now let's look at application of DCT, discrete cosine transform, how it's being used in a standard video. We have here the two popular examples or instance of standard are JPEG and MPEG. Note this. Sometimes it appears in the exam. Video standard or image standard, JPEG. And JPEG means Joint Photographic Expert Group, and MPEG, Motion Picture Expert Group. These are standards that have been agreed, or it has become a law or rules guiding the operations of an image. That is why anytime you work with an image and you want to save it, is either you save it in JPEG or PNG. If it's a video, sometimes you have to maintain this standard. Sometimes we call it extension, file extension. If it's Microsoft Word, we say it's .docs or doc, sometimes docx. If it is a PowerPoint, we say .ppt, and vice versa. The same way it applies on JPEG. If you pick a picture, you want to save it and save it .dos or doc or maybe PDF, portable document file. Instead of you save it as JPEG, you went and save it as PDF. It is no longer the same. So sometimes you lose the file because it cannot open. So let's move on so that you understand the discussion better. Let's look at the two standards. JPEG is a standard for compression of still images or pictures. The color signal, red, green, and blue, are sampled, and each color component is transformed by DCT in 8 by 8 pixel blocks. This operation or approach helps to make your picture smart or be in a good order. The coefficients are recorded, or reordered by reading the DCT coefficients matrix in zigzag form, and the data stream is Huffman coded. We have discussed about Huffman coded before in our previous class. Huffman coded. So it will be in the 8 by 8 is a kind of in the matrix form, but it has no order. It can go up, can go down, just like that. So, but you don't have much to do here. Just note the standard. If you ask, just measure the two standards. So the next standard is the Motion Picture Expert Group, MPEG. We have one, we have two. Just like when you have a video, you see what is normally MP3, MP4, MP5, MP. This is what we are talking about, MP. Sometimes the real full meaning of it is MPEG, but in a short form, we call it what? MP. Do you have MP? You want to play some music, you wouldn't understand what it happens. But as a master student, you should be able to know how this thing works. For example, for compression of a full motion pictures on digital storage media such as CD-ROM or DVD, digital versatile disc, even in your scan disk or flash drive, or in your HDD, hard disk drive, with a bit transfer rate of about 1.5 megabits, is similar to JPEG. With this, standard compression is achieved by allowing sample frame splits into blocks to be transformed using DCT in the same way as JPEG. The same way the picture works, the same way the video works, but they have a different standard. If you pick a picture and maybe put extension .mp or MPEG, that picture will be, you lose that picture. And if you have a video image, instead of you choosing the appropriate standard, you mistakenly use .jpeg. That image, that video, you'll be seeing it, but you can't play because it's the wrong format. So that is what happens then. The next step is wavelength compressions. It first appeared as early as 1980s in geophysical work, but has long spread to other areas, such as, it's no longer, as the first time wavelength compression appeared was in geophysics or geophysical work. But after that, other disciplines such as computer science, mathematics, engineering have to do what? Embrace it. As they embrace it, it becomes a very good concept, just like a Fourier transform. which will decompose a signal into a set of sine waves of a specific frequency. But with wavelengths, the basic functions are not restricted to the sine waves and can be quite different in form and in character. All right, so we have very short time to round up, but before we do that, we'll look at the representations of them. How was this represented in a Fourier transform? Some of the functions are restricted, but in wavelength, there is no restrictions, or not restricted. Okay. Then representation of a signal using sinusoid is very effective for stationary signals, which are statistically predictable and are time invariant in nature. What were we trying to say? That wavelength, all this thing was established for effective in mostly non-stationary signals. Transform are good for dynamic stationaries, but wavelength is good in non-stationary signals. Non-stationary signals, those ones that does not vary or change. You know, when you talk about wavelength, when you are talking, watch the movement of the voice. If you are talking, based on the momentum at which you are talking, you'll be seeing it, the signal will be like this. So that is wavelength. Just like if you are a type that is close to river, and when there is maybe a wave in the ocean, you see it be like turbulence. So that is why when you are talking, the same way, if you want to edit some voice or video or audio, you watch them, all of them are all in wavelength. So that is what we are trying to establish here. We see that wavelengths are functions defined over a finite interval and having an average value of zeros. The basic idea of the wavelength transform is to represent any arbitrary functions as t as superposition of a set of such wavelengths or a basis functions. Let's just look at this. Look at the mathematical transforms as this. If the model wavelength is denoted by other wavelengths for this, where the A is less than 0, remember here, they say that average value of 0. Remember what we're saying here, that wavelengths are functions. See it, defined over a finite interval and having an average value of zeros. So that is why the 0 is less than zeros, and the real number B can be represented as this, what we will see here. So look at the sample of what we are discussing about. As you are talking, the voice will be going up and down depending on their momentum. So all these are mathematically represented as this. So I think the other basic things here, the fundamental concept behind sub-band coding, SBC, is to split up the frequency band of a signal and then to code each sub-band using a coder and bit rate accurately matched to the statistics based on the band. You just see figure 3.6a. So based on this, the sub-band as well as the coding error confinement within the sub-band. Maybe let's look at the figure 3.b. Look at the brightness of the two images in figure 3.6a compare with figure 3.6b, you see the original learner 1 image have been reconstructed to learner with DC component to show blocking artifacts. You see, just watch and this how the image, at least this one, the 3.6 is a little bit brighter than compared to the second one. Okay. In summary, when you are dealing with image and video compressions, it is very important that you know how this works, especially in the digital multimedia applications. Sometimes you have a video or image, and if you want to save it, it will tell you it's too much. So sometimes you use some applications to compress it. When you are compressing it, you are reducing the compressivity. You are compressing it. Sometimes you reduce the value of that image or video. Either you cut part of it, either you remove part of the insignificant details, or what we refer to as noise. What are you doing? You are compressing them. Sometimes image, you check the pixel, the size, you reduce it or increase it. All these things is out of compressing it. But sometimes in the digital multimedia applications, there are a lot of features or tools or applications that can help you do this digitally. So you take note of this, and here we are like try to establish that wavelength theory is also a form of a mathematical transformation compared to Fourier transform. In that order, it takes a signal in terms of what domain, but this one takes more of mathematical representations. Therefore, wavelengths as a component species used to analyze a signal, they are limited. In terms of space, is limited. The ability to vary the scale of functions addresses its different frequencies also makes wavelength better suited to compare to signal with spikes of discontinuities. Especially when you compare it with some conventional transformers or traditional transformations, such as Fourier transform. Fourier transform is more of manual, is more of conventional approach. Wavelength functions is more of digital approach. And application of this wavelength theory includes JPEG, Joint Photographic Expert Group 2000, which is based on the wavelength compression algorithms. This is a standard. Then we have ISO standards. It has been confirmed. It has passed through expert opinion or expert analysis. It has passed integrity test, and it is now widely adopted to be used. So that is the well-known algorithms for wavelength compressions, especially for those who are into graphic design or multimedia applications. They are the people who might find these sections or this topic interesting to understand most of the things they are using their tools to achieve. let them know how it works. However, since it's is compulsory course, is a main course for all of us. So no matter how you can do it, even if to cram it if you don't have interest in multimedia domain, but you must pass it. Even if to cram it for the sake of the exam, please. I don't want any of you to come back again to write this course. Last time I was marking it, so many people are writing it second time, third time. I don't know why. But thank God that at this with what we are doing now, it will be easy for you to remember them. When you read it, to memorize them, at least even if they ask you in the exam, you remember some of the illustrations, the real life scenario we use. Use it, just write. You mustn't write verbatim. So you can use some of the illustration we have here. Just write it as a story to portray your point. And with that, you have your point. You have your full mark. Okay. Other area for further readings have been provided. Thank you for your wonderful listening. If you have any questions or concern, please feel free to share it before we draw the curtain close. Somebody is asking whether you have MSc Information Technology WhatsApp group. We can do better together. Well, the university does not encourage any WhatsApp group. They say you want to do that, you do that on your own and not the requirement. University only provide chat group or what we call discussion group. You have issues there, you relate it. You have issues, you can discuss there, or you reach out to your facilitator via email. So I think that is only enabled platform for now. And again, in the channel where the material be uploaded, in the comment section, you can also share your concern. Your other colleagues are there to interact or discuss some areas or topics that you maybe in one way or the other you could not actually get it clear. So thank you. And
So what about the channel?
I said I will share it via, you get it through your email. So the YouTube channel, someone's asking, I will share it with you via your email. Between now and tomorrow, you get it.
Okay, sir.
So, in the absence of any other thing, once again, thank you for your.
Excuse me, sir. Sir,
Okay.
like you said, there will be lecture tomorrow.
I didn't get you.
Like you said, there will be a class tomorrow.
Yes, I am proposing we'll have a class tomorrow to take the last lecture for day 6.
Okay, sir. What time?
I think let's use the same time, 7 o'clock. How would it be? For I hope, will it be convenient for all of you?
Not actually, sir.
Then do we consider tomorrow is weekend? Can we consider 9 o'clock tomorrow morning?
No, sir.
11 o'clock tomorrow morning?
I think
Yes,
that
okay.
7 o'clock is okay.
Okay.
7 p.m.
Yes.
7 p.m. is better because in the morning there will be 8:07. There might be 8:07. We are not too sure.
Okay. Let's just leave it the same time. 7
We are not sure of that.
7 p.m.
7 p.m. is okay.
7 p.m. I will also send you a reminder in regards. Thank you.
Yes, sir. Thank you.